Okay, so in this problem, we're trying to find the point on a graph that is closer than any other point to the point 3, 0. All right, so we're trying to minimize distance. All right, in distance problems, it turns out that it's easier to work with the square of the distance, and we'll talk about that as we go along. All right, draw a picture. All right, so we've got the graph of the square root function, y equals square root x. All right, and we have a little bug who's crawling on the graph, and they are at some coordinates x comma square root of x. And we want to know of all the points on this graph, so for all x greater than or equal to 0, at which of these points is the bug closer than at any other point to the point 3, 0. Okay. So by close we mean that this distance is small. All right. So we need to find a formula for that. All right. Now if I can make that distance small, I can also make the square of the distance small. All right. Or if I can make the square of the distance small, that also corresponds to make the distance as small as possible. So you can use the distance formula, or you can use the Pythagorean theorem here. Right. This side, the vertical side, we find by taking the difference in the y-coordinates, so square root x minus 0. The horizontal side would be x minus 3. Right. And then we can use the Pythagorean theorem on this nice right triangle here. Right, so my function, which corresponds to distance squared that I wish to max or minimize, is going to be a squared plus b squared equals c squared. We can clean this up. And there's our function to be optimized. So that's step 3. In step 4, we're supposed to eliminate a variable, but we only have one variable at this point, so we're all set there. Step 5, we're going to determine the appropriate domain of this function. Well, as long as x is greater than or equal to 0, then this makes sense. Okay. Step 6 is where we do our calculus steps, so we've got to find where the distance, squared distance, is minimized. So that's going to occur at a critical number, or at an endpoint, but it doesn't happen at x equals 0 because they're on 3 away. Maybe that's where it is, but I don't think it is. So take the derivative, and I get 2x minus 5. If we were working with the normal distance, we'd have a square root on our function here. Okay, and our derivative would be a little more complicated, but we did still end up with the same critical number. So we're going to set this equal to 0, and I get a critical number when I solve for x, or x equals 5/2. Is that the minimum? Well, I need all x is greater than or equal to 0. I'm going to make a sign chart for the derivative here. The only critical number is at x equals 2.5. If I'm to the left of 2.5, then the derivative is negative. If I'm to the right of 2.5, then the derivative is positive. So I have a function which decreases everywhere in its domain until 2.5 and then increases everywhere. All right, and so that shows me that f has absolute minimum at x equals 2.5. All right, now go back and read the question again. Have you answered it? We need to find the point on the curve that is closest to the point 3, 0. All right, I haven't found the point on the curve. I found the x-coordinate of the point on the curve. If I want the point on the curve, I've got to go back here and look at this point. So the closest point is x square root x equals 2.5 square root of 2.5, or 5/2 square root of 5/2.